All right, let's talk about a statistical tool that has a bit of a scary name, ANOVA. It stands for Analysis of Variance, and yeah, it can sound pretty intimidating. But honestly, it's a surprisingly clever way to figure out if the differences you're seeing between groups are actually real, or if they're just due to random chance. So let's break it down.
So imagine this. You're a researcher, you've got 3 new therapies for anxiety, and you really need to know which one works best. Now, you could compare them 2 at a time, therapy A to therapy B, then B to C. But here's the catch. Every single time you run a test, you increase your risk of getting a false positive. We need a much cleaner way to look at all 3 at the same time.
And that better way is ANOVA. Right there in the name, Analysis of Variance, it tells us what it's all about. It's a hypothesis test that's specifically built to check out the mean differences between 2 or more groups at once. This makes it the absolute perfect tool for our therapy problem.
Okay, so here's our game plan. We're going to start with the big idea behind it all, then walk through how it's calculated. After that, we'll figure out what the results actually mean, cover the important rules, and then take a quick look at the rest of the ANOVA family. Let's dive in.
So let's get right into the core logic. And you might be thinking, wait a minute, if we're comparing means, why is it called the analysis of variance? That seems kind of weird, right? Well, it turns out that little contradiction is the secret to how this whole thing works. At its heart, ANOVA is really just asking one simple question. Is the difference we see between our groups a real meaningful effect, or is it just random background noise? And to answer that, it cleverly compares the variation between the groups to the normal random variation that just naturally exists within each of those groups. Let me give you an analogy to make this super clear. Think about 3 different classrooms taking the same test. The between-group variance is how much the average score differs from one class to the next. Are the classes really performing differently? Then you have the within-group variance. That's just the natural spread of scores inside any one classroom. Some students will do better, some will do worse. It's just normal variation. ANOVA just weighs these 2 things against each other. And the way it does that weighing is with something called the F ratio. It's literally just the variance between the groups divided by the variance within the groups. So think about it. If the differences between your groups are really big and the random variation within them is small, you're going to get a big F ratio. And a big F ratio tells you that your result is probably significant. Okay, so that's the logic, but how do we actually calculate that F ratio? Let's walk through the steps. And don't worry, we're going to focus on the why behind the numbers, not get bogged down in a bunch of heavy-duty math. The whole process follows 4 pretty logical steps. First, we calculate the sum of squares, which is just a fancy way of adding up all the variation in our data. Second, we figure out the degrees of freedom, which is basically an adjustment for how many groups and people we have. Third, we use those first 2 numbers to get the mean squares, and that is our official measure of variance. And finally, we just divide the between-group mean square by the within-group mean square to get our F ratio. See? Step by step.
And here's where all that work ends up, the ANOVA summary table. It's a super neat way to organize everything. The sum of squares, the degrees of freedom, the mean squares for both the between and within variation. But the real star of the show is right here at the end, our final F value. In this case, it's 9.61.
Okay, great. We have our F value. We have our number. But what do we actually do with it? Let's get to the payoff. What does this result really tell us? A significant F value is kind of like a general alarm. It's telling you that, yes, a statistically significant difference exists somewhere among your groups, but it doesn't tell you exactly where that difference is. Is therapy A better than B? Is C different from A and B? The F value by itself can't answer that question. To find out exactly where the action is, we have to run post hoc tests. Think of these as follow-up investigations that compare each pair of groups to pinpoint the specific differences. A couple of really common ones are Tukey's HSD test, which is awesome when your groups are all the same size, and the Scheffé test, which is a bit more cautious and works well even if you have unequal group sizes. And this right here is how you'd see it all reported in a research paper using APA style. Notice how it works. First, you report the overall F value to show, hey, there's a significant effect here. Then you specify what the post hoc test found, which exact groups were different from each other. That's how you tell the complete story. Now, like any good statistical test, ANOVA has some rules you need to play by. So let's quickly cover the fine print and what you can do if your data decides to be a little bit rebellious. There are 3 big assumptions.
First is independence, which just means each person's score is separate and doesn't influence anyone else's. Second is normality. The data inside each of your groups should look kind of like a bell curve. And third, homogeneity of variances, which is a fancy way of saying the amount of spread or variation within each group needs to be pretty similar.
So what if your data breaks those rules? Don't panic. There's a backup plan. It's called the Kruskal-Wallis H-test. This is what's known as a nonparametric test, which means it doesn't need to follow all those same assumptions. It basically does an ANOVA on the ranks of your data instead of the actual scores. Pretty clever, right? Finally, it's really important to know that the basic ANOVA we've been talking about, what's called a one-way ANOVA, is just the beginning. It's really the foundation of a whole family of super useful statistical tests.
For example, there's a repeated measures ANOVA, which you'd use if you test the same group of people multiple times, or a two-way ANOVA, which lets you test two independent variables at the same time, like, say, therapy type and gender. An ANCOVA lets you control for some other variable that might be messing with your results. And a MANOVA, you use that when you have more than one dependent variable. It's an incredibly powerful and flexible toolkit.
So when you boil it all down, ANOVA is so much more than just a formula. It's a really logical and powerful way of asking one of the most fundamental questions in research. Is the thing I'm seeing real, or is it just random noise? It's all about separating the signal from the noise. And that's ANOVA in a nutshell. Hey, if this explainer helps you separate the signal from the noise on this topic, I'd really appreciate it if you like, share, and subscribe for more deep dives into psychology and statistics. Thanks for watching.